So let me ask you something. What's more important when you're on a treasure hunt? Actually finding the treasure chest or definitively proving it's not where the map said it would be? It's a really interesting question, right? And today, we're going to see why in the world of physics, that second answer, well, it can be every bit as exciting as finding gold.
Right, let's dive in. We are talking about the science of nothing. I know, it sounds weird, but we're exploring how experiments that come up empty, the ones that don't find any new shiny particles or forces, are actually some of the most critical discoveries we can make. They are, in a way, the silent heroes that push all of science forward.
To really get why finding nothing is so huge, we have to start with this grand quest humanity's been on for centuries, trying to create a complete map of reality. You know, just a small project, figuring out the fundamental rules that run absolutely everything. And our best map, by far, is this thing called the Standard Model of Particle Physics. And when I say best, I mean it's ridiculously, unbelievably successful. This theory describes pretty much all the fundamental particles and forces we know of. Everything from the light coming off your screen to the sun in the sky, it nails it with breathtaking precision. It is literally the most accurate scientific theory humans have ever dreamed up. But, and this is a huge but, here's the catch. We know for a fact that this beautiful map is incomplete. There are massive parts of our universe that it just can't explain. It's kind of like having a perfect street-level map of London and Paris, but the map is completely missing, North America, South America, and Australia. So what continents are we missing? Oh, just some minor stuff like gravity? The standard model has nothing, and I mean nothing, to say about it. Or dark matter, the invisible cosmic glue holding our galaxies together. Or dark energy, the mysterious force that's making the universe expand faster and faster. The point is, scientists know there has to be some kind of new physics out there to fill in these giant gaping holes. And that brings us to our first case file, the hunt for these missing pieces at the tiniest scales imaginable. So how do you find a flaw in a theory that's almost perfect? Well, you push on it and you push on it until, maybe, it breaks. And that's exactly what's happening at the LHCb experiment at the Large Hadron Collider. You can think of these physicists as cosmic detectives. They are smashing particles together at nearly the speed of light just to see if the shrapnel flies apart in some weird way that the standard model, our map, says is absolutely impossible. They're basically stress testing the source code of the universe. Now, one key idea they're testing is called lepton flavor universality. Okay, yeah, that's a mouthful, but the concept is actually pretty simple. Imagine electrons and their heavier cousins, muons, are like identical twins. The standard model predicts that the universe should treat them exactly the same. So if a particle decays into an electron 100 times, it should also decay into a muon 100 times. The universe isn't supposed to play favorites. So the LHCb team ran this incredibly specific test. They were looking for a particle, a B0 meson, to decay in a very particular and very forbidden way. According to our map, this specific decay just plain shouldn't happen, ever. Finding it would be like discovering a fundamental crack in the foundation of modern physics, a total game changer. So after sifting through mountains and mountains of data, what did they find? They found this. No significant signals are observed. They found absolutely nothing. The forbidden thing didn't happen. A null result. But this nothing is one of the most important somethings you can imagine. I mean, look at this number. The team proved that if this forbidden decay ever happens, it's rarer than 1 in 10 billion. It's just an unbelievably small chance. So this isn't a failure, it's a massive success. They didn't find a crack. What they did was prove that the foundation, right here, is rock solid, forcing all the other treasure hunters to go look somewhere else. Okay, so our map holds up at the smallest scales. But what about the absolute biggest? Let's jump to our second case file. We're going from the extremely tiny to the unimaginably massive, listening for whispers from the cosmos. The LIGO-Virgo-Kagra collaboration, these amazing gravitational wave observatories, are basically doing two incredible things at the same time. On one hand, they are searching for the complete unknown. They are trying to hear faint, continuous ripples in spacetime that could reveal hidden objects we've never seen before. But on the other hand, they're testing the known. They're watching titanic black hole collisions to see if they follow the rules laid down by geniuses like Einstein and Hawking. And one of those big rules is Stephen Hawking's area law. It's a fundamental principle of black hole physics that's actually pretty straightforward. It just says that the surface area of a black hole can never, ever get smaller. So when two black holes merge, the new, bigger one has to have a surface area that's at least as big as the two original ones combined. Simple, right?
And the results perfectly show the two sides of discovery. In that big search for new hidden neutron stars, a classic null result. No periodic gravitational wave signals were observed. They looked everywhere and found nothing. But when they tested Hawking's law using a real-life black hole merger, a stunning confirmation. The law held up perfectly. So, we've got two huge, ambitious searches for new things, and both came up empty. And you might be thinking, well, that sounds kind of disappointing. But no, this is where we get to the real heart of it. Understanding the profound, powerful progress that comes from hearing the universe tell you no.
See, finding nothing is not a dead end. It's the exact opposite. Every time an experiment like these confidently rules out a possibility, it makes what we do know even stronger. It's like telling all the other scientists, hey, don't waste your time looking for treasure over here. We've checked. The map is correct in this spot. Go look somewhere else. It actually narrows the search and makes our whole foundation of knowledge that much more solid.
So you have to wonder, right? Who are these explorers? Who are the people making these unbelievably precise measurements of, well, nothing? Just look at this. This isn't just a bunch of names. This is the author list from just one of these physics papers. We're talking about thousands of scientists from hundreds of different institutions all over the world, all working together to get a single, hyper-precise result. This is the monumental human effort that it takes to be able to stand up and say, with total confidence, we looked here and there is nothing to be found. It's incredible.
So this is how science really moves forward. You see the pattern? We take our best maps of reality and we test them like crazy. Sometimes the test confirms the map is right, and that deepens our knowledge. And other times, the test proves, with amazing certainty, that the treasure isn't where we were looking. That null result closes off a wrong path and forces us to search in new, more creative directions. Both outcomes are win. In the end, I think it helps to imagine that the edge of our knowledge isn't a cliff we just fall off of. It's more like we're all standing in a vast, dark room. Every null result, every time an experiment finds nothing, it's like striking a match. It doesn't instantly reveal the answer we were looking for, but it illuminates a corner of the room, proving it's empty. It eliminates the shadows, and it brings every single one of us one step closer to finding the light.